Hello guys, welcome back to my channel DP Design, and in this video we are going to perform a basic static simulation of a beam, and let's get started. So first you can see the welcome window over here. So you have to choose what kind of simulation you want to perform. If you have a database file, you can open from here. If you have a Python file, you can run the script from here, and if you want to start a tutorial, so it will take you through their blog. For now we have to create the first standard or explicit model. We have to go with this, and you can click the OK. Now you can see this is a message window where you can see the what is happening right now in the background, right? So the model has been created already. This is a model 1, and you can create the multiple simulation over here. Now this is our model tree, and this is our module window. So in the module window there are the options which are common in CAE software, like you have to create a part, you have to apply the material, you have to apply the what kind of simulation it is. It is a static, dynamic, or dynamic temperature displacement, heat transfer analysis, explicit or implicit. So those type of simulation you have to give to the steps. Then you have to apply the interaction. If there is an assembly, then you have to apply the context, you have to apply the frictional coefficient, film coefficient, etc. Then you have to apply the load, meshing is there, optimization is there, and you have to apply the job for running the simulation, right? The solver will do that job. And visualization is there, which means a post processing of our results. So you can start with the part. You can also perform the simulation by giving the boundary condition from over here. I prefer model tree to better hands-on UI, right? So let's start with the part. As it is a basic simulation, let's say I'm applying a 2D simulation for now. So 2D static beam simulation, right? I will select the 2D planar, I will apply as a deformable, then I will select the wire. Okay, this is the approximate size of our play area, right? Okay, invalid name is there, so this should be as a beam only. Okay, now you can create the line just like in every CAD software, right? You can apply the dimension from here. Let's say I will apply the 135. I will cross. Okay, done. You can see my part has been created, which is a 2D beam, a one single line, and you can see there is a beam has been created already. Now I will go to the property. You can apply the material from here. Also you can do the operation from here as well. So what you can do, you can create the material. Let's say I am applying the material as a steel. I will create. You can apply the description, and I will create the density of 7800 kilogram per mm cube, and apply the Young modulus from elastic 2 raised to 11, sorry, 2 into 10 raised to 11. Then Poisson's ratio is around 0.23. Okay, so you can see my material has been already created. Now you have to create one section which is having a material of a steel, so I can assign the section of steel to this beam, right? So you have to create one section, then I will apply the section name, let's say beam and the steel. This is the homogeneous, but one thing I have mistaken over here. What is that? I have applied the solid. My part is not having the solid geometry or cell geometry. So what you can do, you can create the beam, and yes, beam 1, and you can select the type. There is a beam. You can select the Poisson ratio, which is having a 0.23, and you don't have profile to select, right? So what you can do, you can create the profile from here. let's say I'm taking the pipes and I'm giving the dimension of 2 mm and thickness of 0.2. Okay, my profile has been created, profile 1, which is having a circular geometry. Then stiffness is there. If you have any stiffness data, so you can import that data into this portion. And if you have performed any CFD simulation, so what you can do, you can apply the inertial fluid effects into this portion. I don't have those data right now, so I will click the OK. My section has been created, which is having the name beam 1. So you can assign the section to this one. What you can do, you can create the assign section and create the set. I will select the set. Yeah, okay. You can see my geometry having the green color now. So what does it mean? That the material has been already applied to this beam, right? Now you have to assign the beam orientation. I will select the beam as it is coordination system. Okay, is not having some kind of bend or round shape, right? So I will apply the orientation as it is. Now you have to create the assembly. Now assembly will create the instances which can be included to the simulation part. So what you can do, you can select the parts and you can select the beam, and then independent and independent. Dependent means you can create the mesh in a single part only. This is the limitation of dependent. And in the independent, you can create the meshing in an assembly. And one thing is that if you are copying the dependent part, then the mesh will automatically copy from that part. So you don't have to mesh that geometry again. And in the independent, you have to create the mesh independently. So this is the pros and cons of dependent and independent. In future videos, we will talk about this in deep whenever we will perform a assembly simulation. Right. And I will create OK for now. As an example, if I'm creating the instance, so I will do auto offset. Then you can see there is a beam creator over here. If I apply, then the beam will stay here for the simulation. Now you are done with the assembly. Now you have to create the step. In the step, you have to specify what kind of simulation you will do. So in the step, you have to create one. Then let's say I am creating a static simulation, right? So you have to select the static general. Okay. You can apply the total time period. Time period will not affect in the static simulation. It will directly affect in dynamic simulation, because everything that changes with time, it will be transient or dynamic, right? So in static, there is no need to change the time period. It is worse. If you have the non-linear geometry, then you can turn the annual geom off on, right? So it will directly include the non-linear effects of the material. I don't have any non-linearity data right now. So maximum number of increments, let's say approx 10,000, and minimum increment size is 0.1, which is my load scaling, right? And maximum load scaling, my 0.5 I will take. And this is the minimum value. Initial value should be a 0.1, because that's why it can be called as a quasi-static, because it is applying the load very slowly. So I will click the OK for now. So you can see my second step has been created. We will discuss in deep about the steps in future videos, so you can get the clear picture. Now we are done with the step. There is no interaction with any other body, so we will skip this and we will directly go to the load. Now in the load, okay, before going on to the load, we have to fix this, right? So what you can do, you can go to the boundary condition. You can select the initial. In the initial, you can select the displacement, and you can lock every degree of freedom. Or else what you can do, you can go to the symmetry or encaster, go to and this one. Okay, I will select the encaster which is having u1 u2 u3 means x y z, and these are the three rotational axes, right? Rotational moment. So ur1 ur2 ur3 is 0. So in all direction it is fixed, right? Now I will apply the load in a static step, right? Whatever fixtures you are going to perform for a basic simulation, you have to apply in initial, and whatever load you are applying, that will be in the next step. And in the concentrated force, I will apply to this one. Okay, now in the y direction I have to perform in a load direction in the y, right? So I will take a, if you are applying the oblique loading, then you have to apply the CF1 and CF2 both together as a resultant, right? It will create the resultant forces. So in the CF2, let's say I'm applying the minus 500, right? In the XY. So minus 5 will be downward direction. If you have any amplitude that is changed with step time, you can apply the amplitude from here over here. I will discuss that later. Okay, now you can see I am done with the boundary conditions. Now I have to match the geometry. Now, yes, if I will try to match the part directly, then it will not get matched. Just like this, it will create an error because you are in assembly, and in assembly you can create only mesh in independent parts, right? So what you can do, you can go to the select parts and you have to apply the mesh to every part. Let's say select the beam, then beam 1, beam 2, and you have to apply the mesh independently. Okay, so if you want to refine the mesh, you can go to the seed part and you can apply the seeding over here. Let's say 14 is very coarse. If you are spending money on your processor, then you can 0.0001, that kind of size you can give. This is 0.4, very fine. I don't want that right now. Let's say I'm taking a 5. Now you will get the mesh part done. Okay, 27 elements have been generated on the parts. Okay, better. Also you can define the type of elements are there. So if you are performing the standard, then you can click the standard and linear, right? Quadratic is not there right now. So if you are applying the simulation of explicit, then you can create the explicit, right? For now it will be standard, and yes, hybrid formulation is not there. Shear flexible, yes. Okay, done. Okay, now I am done with the meshing part. Optimization is not I'm doing right now. So what I can do, I can create the job. Yes, before job I want to specify one thing. Then wherever you want to save your result, you have to set what directory over there. Let's say I am saving my result to trash and Abaqus. This is my name. Okay, wait, the directory one, and I will select the directory. Okay, and yes, you can create the job from here. So if you have any input file from ANSYS, Nastran or any other software, you can apply the input file from there on which you have given the boundary condition and run the results over here. Now I don't have any input files, so what you can do, you can just perform the simulation. Yes. Create In the memory, I will select my processor R2, but for now there is no needed. Okay, done. Now you have to submit the job, so you can click the run. Okay, now you can monitor your data. If you don't have any like enough tokens to see the result, then you have to close the software and see the results in your file. OBD output is there, data file, status file you have to see. The analysis has been the same file will be created in the directory file. Let's say I am giving the desktop and trash directory 1. Now you can see my status file is there. Yeah, so this is my attempts. In one attempt, every single increment has been done in a one attempt, and this is my step, which is having an increment of 0.1, and my analysis has been completed already, right? So if you have any error, you can find that in a data file. It will show you the error here after the process or before the process. It will show the error that your element is not good, your context is not good, etc. Right? And you have this IMP file which can be run in ANSYS, Nastran, or whatever simulation software, right? So I have completed this. Then okay, I will go to the visualization. Yes, and you can create a path. Now you have to open the ODB file from here, and you can see the deformation, right? You can if you want to see the animation, so here is the option of animation. So yeah, you can slow this down, and if you want to see the beam profile, right? So what you can do, you can go to this and you can select the render beam profile and apply. So this is the profile I have given in the beginning. So what you can scale this also. Let's say I want to apply the 0.5. If I want to show this very thin or thick, then I have to apply the 5. Yeah, this one is very bigger. Now I have some maximum like if I want to up, yeah, this is the U means displacement, and this is the primary default. If you don't know these terms, then you can directly click on this and it will show you the point load at nodes, right? This is the concentrator force at nodes, and reaction forces you can give, the reaction moments at node you can study. So these are the data you can study over here. In the next video, we will study about the like XY data, right? How you can apply the force versus displacement data, how you can interpret the results better for the optimization purpose. So this will directly come to the next future videos. Till then, you can support our channel, subscribe, like, whatever you do, we will keep sharing our knowledge. And thank you. Keep sharing, keep loving.